So today we will start elasticity. So elasticity is a mechanical property of solids. So before starting elasticity, let us know what are rigid bodies and solid. So a rigid body, what is a rigid body? A rigid body is a structure where the atomic distances are fixed. You can say interatomic distances are fixed. So on application of force, the distances remains unchanged. So this is a rigid body. But practically there are no such rigid bodies. All solids are considered as rigid bodies ideally. Got it? So all solids are actually considered as rigid bodies ideally, but in reality they are non-rigid. Why? Because say if we apply forces on the solids, their interatomic distances changes. So you will see that the interatomic distance changes and on the changes and they get deformed, but on removal of these forces they get back to their original positions or configuration. Now what is configuration? So here configuration means shape and size or the arrangement of atoms in a solid. Now we come to the definition of elasticity. So definition. So what is elasticity? So elasticity can be defined as a property of a body by which it can recover to its original configuration, that is shape and size, on removal of the deforming force. So elasticity is the property. So elasticity is a property by virtue of which a body tends to recover its original configuration, that is the shape and size, on removal of the deforming force. So suppose if we apply force on a body, so by using this force we can change the shape or size of the body. But on removal of these forces, the deformation goes away, and what happens? A restoring force develops to restore the original configuration of the body. This property by which a body can restore its original configuration is actually called elasticity. Fine. Now the these types of bodies which exhibit elasticity are called elastic bodies. Fine. Elastic bodies. Now in similar way, the bodies which cannot recover. Now bodies, suppose if cannot recover its original configuration and remains deformed. So it remains deformed even after removal of the forces, then such bodies are called plastic bodies. Such bodies are plastic bodies. Such bodies, plastic bodies, and the property is called plasticity. The property is plasticity. Fine. So now we came to know about what are plastic bodies and what are elastic bodies. Fine. So Ityasaba, what are the main cause of this elasticity? There has to be some internal cause which causes elasticity. So then we'll see that all this is because of some atomic level forces. Fine. Say in 3 dimension, this is the arrangement of atoms. Fine. Arrangement of atom. My drawings are not good, doesn't matter. So basically here these circles are atoms. Fine. And all the atoms are connected, actually are bonded by elastic bonds. So here we represent each bond as a spring. Why? Because these bonds actually acts as spring. So as we know, what is the potential energy of a spring, you will come to know in simple harmonic motion. It is given as half kx square. Fine. Now this is half kx square. This can also be written as half k x minus x naught square, or this one. See, this is the 3-dimensional arrangement of atom. Suppose if we can take a single section, say this part we can say this is one atom. Suppose it is fixed and it is connected to another atom by a spring. Now with respect to this atom, suppose if we sit on this atom will be static. Fine. Now this is at a distance, say x naught. This is the equilibrium distance. That means under when there is no force acting on this system, the atom, suppose this atom is at a distance x naught from here. But suppose if we stretch this atom from here to say here, to a distance say x, then the potential energy becomes half k x minus x naught square. Fine. This is the potential energy. Similar way, if you compress this atom here to here, say here, fine, same thing will happen here. You will be half k x naught minus x. So this is the potential energy. Now as we know, this potential energy will give rise to a force which is given by du by dx. It's like du by dr. Here it is x because I am considering only one dimension. Fine. So for one dimension it is du by dx. So this is correct for conservative forces. So the force developed in the spring due to the compression or extension of the spring is a restraining force, and that force is conservative. So what are conservative forces and what is the relation of conservative force with the potential? Potential লগত কি relation থাকিব conservative force or you will get to know in when you are studying force and potential. Fine. এতিয়া চাবা যে এতিয়া যেতিয়া আমি ডিফারেন্সিয়েশন কৰিম কি হ'ব, that is half of d dx is half. So when we differentiate, what we will get, that is half k x minus x naught square. What we will get, you can do it yourself. Here it will be half x minus x naught. So f equal to negative of k x minus x naught. So as you can see, what will be the force if the atom is stretched? So this is x, this is x naught. X minus x naught is positive. So when x, say when x is greater than x naught, f equal to negative, that is attractive. So whenever you pull this one, stretch this atom, a attractive force will be generated, as a result of which the atom will be pulled in this direction. It will be pulled toward the equilibrium position. Now if the atom is, instead of stretching, if you compress it, what will happen? Then the x is smaller than x naught. So if you compress, say when x is smaller than x naught, f will be positive, that is repulsive. So when you compress, the force generated will be repulsive, that is it will again try to move toward the equilibrium position. So the force generated during a stretching or compressing of a spring is such that it tries to restore its position in equilibrium position. That's why it is called restoring force. So direction of the restoring force is always opposite to the deforming force. So restoring force is always opposite to deforming force. Fine. So this concept you should know, how a restoring force is generated. Only when there will be deformation due to a deforming force, restoring force will be there to restore its original configuration. Fine. Now the same thing what I have told you, I will explain in a diagrammatic manner. How? Say, this is the potential energy versus position. Fine. R or X, you can say X. This is X naught. This is the X direction. Now that you can see, this is the potential energy structure of what? The potential energy structure of the elastic bonds between the two atoms of any bonds. In the 3D structure, say here it is connected to four atoms. This atom is connected to 4 atoms. So each atom is connected by elastic bond, and the property of the elastic bond, property of the potential energy of the elastic bond is represented by this graph. Actually here the potential energy is equal to half k x square plus bx cube plus cx to the power 4, like this. This is the actual structure of the potential energy of elastic of the bond. But for very small, x is the extension from the equilibrium position. X is the extension from equilibrium position. So for very small x, we can neglect this cubic and x to the power 4 terms. So potential energy is half kx square, or for this graph, half k x minus x naught square, x minus x naught square. So this part is called harmonic part. Simple harmonic motion you will see like this. So this is harmonic part. This is enharmonic part. So we leave out the enharmonic part. So for harmonic part, the potential energy is given by half k square. If you plot this one, you will get this type of graphs. Now the point to consider is that, suppose when the position between the distance between two atoms are x naught, the potential energy is, this is potential energy minimum. Fine. Now as you know that every atom, every system actually wants to be in minimum potential energy. This is the most stable state of a particular system. So it always wants, a system always wants to be in minimum potential state. For this system, the minimum potential state is when the interatomic distance is x naught. Now suppose if we apply a force and increase this interatomic distance from x naught to say here is corresponding energy is P1, and here suppose if we compress it till this point, it is suppose P2. Now this one is suppose x1, this one is suppose x2. Now potential energy P1, it is at x1, it is what? Extension. So extension P1, this potential energy is greater than P minimum. So a system will always try to get to the minimum potential energy. So what will happen when you stretch, when the bonds are stretched till here, what will do, a restoring force will be created which will try to pull the atom till it gets to x naught, the equilibrium position. In the similar way, if you compress till x2, what will the corresponding potential energy is P2, which is greater than P minimum. So in order to get to P minimum from P2, what the system have to do, a restoring force will be developed which will push the atom from x2 to x0. So in both cases, what we will see, a restoring force is developed in the direction opposite to the direction of the deforming force. Fine. So for compression P2, that is at x2, it is also greater than P minimum. So in both cases, the system will try to get to P minimum. So in both cases, P1 and P2 will try to achieve P minimum, that is to get to x naught. So a restoring force is developed to against the deforming force to restore its original